neutrinos, and then we will switch to accelerator experiments. And I will discuss first acceleration of particles. So neutrino has been discovered in 1956, although kind of final date of discovery, although the experiments were between 1953 to 1956. And the names of discoverers are Reines and Cohen, Frederick Reines and Clyde Cohen. Let me remind you that the story of neutrinos started in 1930 when Pauli made this hypothesis, and people discuss a lot if this is real particle or not and how to detect it. And I said already that that became possible after atomic reactors were constructed and new methodics of the detection, in particular using of scintillator detectors and scintillator technique, that was allowed to detect neutrinos. So remember, the first discoveries made with quite small devices, like for instance, these Wilson chambers used to discover muon and positron were of this size, 16 centimeters diameter. So the further progress you will see is toward creation of bigger and bigger detectors. So not only you need to have big mass of the target, you need also to have good way to look at this target and to see what's going on inside. So remember also that one of the proposed reaction to detect neutrinos was inverse beta decay, when electron antineutrino scatters on protons and produces neutron and positron. Pontecorvo, who also thought about the detection of neutrinos, has proposed another way using chlorine. I will discuss this later. But in these experiments, inverse beta decay has been used, and this is the reaction which was predicted on the basis of Fermi theory. Remember, Fermi theory was constructed to describe beta decays. However, the same Lagrangian predicts also some other processes, and in particular this one. That time also a criteria of detection of neutrino, which doesn't left any, say, tracks, has been formulated, and that means that you need to detect this particle somewhere outside the production region. So you need to have detector, and you need actually to prove that this particle can transfer momentum, energy, and quantum numbers. That would testify that neutrino, although not seen directly or kind of not leaving the tracks, is a real particle. So the detector, by the way, let me add that this reaction has a threshold which is 1.8 MeVs, which is essentially made of difference of masses of proton and neutron. And this difference is 1.3 MeVs. This is the difference of masses of proton and neutron. Neutron is heavier, plus the mass of the positron, which is 0.5 MeVs. And so the threshold is 1.8. This means that you need to have neutrino energies bigger than 1.8 for this reaction to proceed. Now let me draw the detector, or the setup, experimental setup. This is setup which was used in the second series of the experiments. It was different equipment in 53 in the beginning, but in 56 the data had been published using the following detector. Let me draw in and then I will explain details. So now the size of the detector is something like 1 meter cube of all the size of volume. The length is 1.9 meters. Then there are 3 blocks with scintillators. These are scintillators. Tanks filled in by scintillators. And the size of the tank is, this is 1.9 meters, this is 0.6 meters, and the width is 1.3 meters, just to have an idea what is the size of this detector. Now, in between of these scintillator detectors, there are layers or tanks with water. So the target is water. Why water? The water is the kind of the substance which contains proton. You can neglect, of course, this binding energy in this molecule. So essentially, the water is composed of oxygen, of course, and free protons. And the mostly process is going on to the protons. For oxygen, also this process can go with oxygen, but you need to have much higher energy because the nucleons are packed in the oxygen. So what else? The width of the water is quite thin, it's 7 centimeters. And this is because you want to have the particles which are produced inside the water to have a possibility to leave this. So you shouldn't have too big widths of this. Now, you have the scintillator detector, and you want to see what's going on inside the scintillator. Remember, so scintillator acts as converter of high energy particle energy releases to ultraviolet. And ultraviolet is well detected by photomultipliers. And on the surface of these tanks, photomultipliers were attached. Photomultiplier tips, which then convert the signal, ultraviolet signal, to the current, to the signal, electric signal. So let me remind that what's going on. Ultraviolet radiation is emitted by excited atoms and the excitation. So this radiation produces photo effect on this plate here, and then there's enhancement of the signal flux of electrons because you have here positive plates. This is cathode, and then anode collects this current, significant signal. What else? So it's not only so water. Here, what is added is cadmium salt, cadmium chloride 2. It's dissolved in the water, and this is to have better detection of neutrons. So this is important component even present-day experiments with reactor neutrinos. What else? Now this detector has been placed at a distance of about, say, 10 meters from the reactor in Savannah River. So let me have here the place. In US. And so neutrino flux was from this side, it's heating, passing through the detector. So this reaction is very nice because it gives a possibility to detect both final products of the process, both neutron and positron. And this is important to to extract this process from the background, which is usually quite high. So the signal has two components. One is what we call prompt signal. And this is due to positron. So what positron is doing, it loses the energy, and the energies are several MeVs, it's above 1.8 MeV, so several MeVs. This is threshold energy, but positrons have energy, say, in the range from 2 to 10 or 8 MeVs. So these positrons at these energies in water, in oxygen, so they lose the energy by radiation. So you do not see this essentially radiation. You can see Cherenkov radiation, and this is what is used in many other detectors. But here you do not see essentially this weak radiation which is due to ionization. So what you see is the following. The positron slows down, and it annihilates with electrons in the medium, producing two gammas. So the reaction is like this. Someone knows what are the Feynman diagrams. So this is emission of two photons when we have annihilation E plus and E minus here. So you have these two gammas, and let me write the diagram. So neutrino hits somewhere here proton, and it emits electron, which annihilates and produces gammas. These gammas enter the scintillator detector, and they are detected as I explained before. So this is fast process. Electron annihilates, it gives two gammas. This is what is called prompt signal. The second one is the signal due to neutrons. So what happens with neutrons is the following. Neutron scatters, and there's multiple scattering of neutron. It's neutral particle, it's not very efficient. And then it mostly, with highest probability, is captured by cadmium. Cadmium becomes excited and produces many gammas at the excitation. So this is what is called delayed signal. Delayed signal. And delayed because it is some time for neutron to meet cadmium nuclei and to be absorbed. The process is like N plus cadmium, and cadmium is known as a nuclei which has a very high ability to capture neutrons. So cadmium becomes excited, and then it has de-excitation with emission of several 3-5 gammas plus cadmium. And so eventually scintillator detector detects these gammas. This is delayed signal. And so what you expect to see two electric pulses. So this is time, and this is the signal, electric signal, current essentially. The first one is due to annihilation of electrons. This is prompt. This is due to positron. And then with delay higher signal, with higher intensity, is due to absorption of neutron. Typical time interval between these two pulses is something like so the signal is something like 1 microsecond. I have somewhere precise numbers. Oh, sorry, 10 microseconds. I have found the numbers. About 10 microseconds. And microseconds is 10 to the minus 6 seconds. So this is typical interval. Of course, it can fluctuate from event to event. Now, the energy release here is, when you annihilate electron and positron, is 1 MeV, around 1 MeV. It's energy release. Here the energy release is much bigger, from 3 to 10 MeVs. So this is what we call a signature of the signal. Signature of appearance of neutrino is, of interaction of neutrino is this 2 pulses effect, separated by 10 microseconds, and with this energy. So one is around 1 MeV, another is higher MeV. This allows to put out these useful signals from background, because they see these pictures with many signals. They detect actually this device produces noise and many other signals. But this is typical for neutrinos, and the background is low. So even detecting several signals of this type tells you that you deal with neutrinos. So it was something like several tens of events detected, on the basis of which it was conclusion that finally neutrinos were detected. And so Reines got Nobel Prize in '95. Well, actually what is important, not only to see this signal, but also to be convinced that the rate of these signals is what you expect. This is important. So you made already computations of cross-section, and now knowing this configuration, knowing the number of volume, so probably you did even estimations, you can compute what is the number of events expected in this case. And so the story was like, that time people didn't know well what is this V minus A theory. It's just about the same period when V minus A theory of parity violation has been discovered. So there were some uncertainties in computations of the number of events. And there were some estimations of how many events should be seen. And on the basis of measurements, Reines concluded that the number of observed events corresponds to number of expected events. However, the theoretical computations were done later, again, and the prediction was changed. And then Reines said, okay, no, my data actually are in a good agreement with these new estimations of the cross-section. Actually, that was probably the reason, this is what people are saying, that he got Nobel Prize so late. So he got Nobel Prize in '95, after Nobel Prize was given for discovery of the second neutrino, muon neutrino, which was later. Okay. I don't know if a Nobel Prize, they should all, no, we need to have still 50 years to see what are these archives of a Nobel Prize committee when they explain what's going on. Anyway, so we don't know what is precise reason, but that was kind of unpleasant situation. So you need not only detect this, but also be convinced that the effect is in agreement with what you are expecting. Questions?
So could the neutrino also interact with the scintillator, because
sure.
It has succeeded. I mean, except, huh?
Yeah, but the number of events here is much bigger.
You can do the computations.
Yeah, sure. Of course, people did these computations. Yes.
Neutron. I don't know if you mentioned, but what are the walls of the detector made of?
Sorry?
The walls of the detector. What is the material of the walls?
Oh, so this is good question, but probably this is done with some metal, because here you need to still have something like plastic or something like this. You need to at least in these places. This can be water, and of course the question is, can you have even some signal if it is iron? No, that has been estimated. I don't know precisely. I can check what was the material used here. But in some cases, you need to take into account also interactions with walls of the detector.
You need some material that reflects the photons, so they reach your PMT.
I'm not sure that probably you need to have here something which reflects photons or to focus. I don't know precisely if they used in this detector.
And these PNTs are double-ended, like in both
Well, I
sides?
think they are surrounded everywhere. So I just put it here, but of course it's here, and also there are photomultipliers from all the sides.
Was it possible to reconstruct spatially the event by time?
Yes, they of course detect the time, because you see they have.
Can you reconstruct the position of interaction?
To some extent you can, but for this I don't think this was important, at least for this experiment.
We do know that the neutron absorption cross-section is also higher for boron, so can we use boron?
Notice cadmium, which is heavy nuclei, it's more efficient, and so that was in the first experiment, but later people used also gadolinium, and in the present day experiments mostly people are using gadolinium for detection of neutron. Also, actually neutron can be captured by proton with formation of neutron, but the signal is weaker, and actually, but even this signal has been detected. So with this capture. More questions? So what I want to add is that the story with studies of reactor neutrinos continued all this time, starting from this discovery of neutrinos till the present. And so this is one of the very active areas of research. I mentioned already that only recently people realized that the computations of fluxes of spectra of reactor neutrinos was not quite right. Still we have, say, 5% misunderstanding or not good understanding of the fluxes and even shape of the spectrum with some bump which was not thought about before. For these early experiments that was not very important, but for present day experiments this is extremely important to know. So let me mention what are kind of further developments in this area. Some of you may work on this stuff later. So what are follow-ups? So later it was a series of experiments, again with reactor neutrinos in 80s and 90s, and the experiments were in Gösgen, France, Bugey. France has many reactors. Then in Russia, Krasnoyarsk, in Siberia, Rovno, and again Shoes in France, Palo Verde in the US. So the goal of these experiments was to study the scattering of neutrinos or antineutrinos on electrons and on nuclei, study cross-sections to a large extent. In particular, mu-E interaction has been detected. Not only scattering on protons, but also on electrons. This was a very important point. And then people start to search for oscillations of neutrinos. Some of these experiments made searches for oscillations. So what is this? So if neutrinos have a mass and they are mixed, we discussed mixing of currents, but I mentioned already mixing of quarks, but also later it was discovered that neutrinos also mixed. One of the consequences of this mixing and non-zero masses of neutrinos is the oscillation process. When one neutrino species, here we are talking about one neutrino only, but then a muon neutrino has been discovered, and already the process of transformation of electron neutrino to muon neutrino was expected. So observation of this oscillation effect, and that should be periodic, so that you have periodic transformation of one neutrino species in another one. This is what we call oscillations of neutrinos, Layer oscillations of neutrinos. And the goal of some of these experiments was to search for oscillations. Because if you observe this, then you can measure what is the mass of neutrino, and to be convinced that neutrinos are mixed particles.
If you have a neutrino electron scattering, what are the final products of such a reaction?
You get electron. For these energies, it's nu E go to nu E. So actually, it's nu E bar go to, so scatter on electrons, go to nu E bar plus electrons, and you detect a recoil of electron.
It's just a scattering.
And this is scattering, and the goal was to measure cross sections of these processes. Well, actually, what is interesting, and I will tell you later, so this process actually has two contributions from charge current, which we know, but also from neutral currents. It was non-trivial, actually, to see and to measure these cross sections. Extremely important experiment was Kamland. In 90s in Japan, and so what they have detected, they detected the signal from many atomic reactors in Japan. Before Fukushima disaster, there were many atomic reactors around the place Kamioka mine where they have this detector. And what they have detected, they discovered so-called 1-2 mode of oscillations. So now we know there are 3 neutrinos, and you have 2, so 1, 2, 3, and you have 2 mass splittings, 1, 2, and 1, 3, right? Independent mass splittings. So they have discovered oscillations with this 1-2 mode, 1-2 mode, 1-2 mass splittings, which actually confirmed what we saw from solar neutrinos. So this was the second important phase of discoveries. Then later, already close to us, this is 2010 and later, 3 experiments have discovered 1-3 mode of oscillations, and those are double shoes. In France, then Diabei in China, and Reno in Korea, South Korea. So these experiments, again reactor experiments with powerful complexes of atomic reactors with much higher power and with bigger detectors. I will show you the pictures tomorrow. Actually decided to show the slides tomorrow. So what they have discovered is oscillations, 1-3 mode of oscillations. So let me probably remind the spectrum of neutrino masses may look like here. These are the masses. This is 1, 2, 3. And the 1-2 mode of oscillations has been discovered by Kamland, and 1-3 by these 3 experiments, with the highest statistics in Diabei experiment. Now, what is the future? The future is Juno experiment. Now, 2-3 is, they are not independent, right? So once you know what is this, you know what is this.
You can do it.
But you can do this independently if you want. Yeah. So the future is what we are now discussing is Juno experiment. Juno in China. And this experiment is aimed to establish mass hierarchy. So this is mass hierarchy of neutrinos. What is this? So you may have the picture like this. However, what is not excluded? The situation like that. Because these oscillation experiments, they're not sensitive to sign of this delta M, and so you still can explain the data if you have 1, 2, and 3 is the lightest. You see it's kind of partially inverted hierarchy. So this is normal hierarchy or ordering, correctly to say normal ordering. And this is inverted. Inverted ordering. And Juno experiment is aimed to establish the difference between these two. Just to give some idea, so this experiment actually starts somewhere probably in 2023. So now it's under preparation. And so the size of this detector is 20 kiloton of scintillator. In Ryan's experiment, the volume of scintillator was about one ton, most, even less. Okay, right. So that size of that, less than 1 ton. And this is 20 kiloton, which means 2 10 to the 4 tons of material. The distance from a reactor complex is something like 50 kilometers. And this is selected because it optimizes the difference between these two situations.
What is the parameter they measure to differentiate?
So you see, maybe I will not explain in details now because that's kind of involved. What they will see modulations. So you have two modes of oscillations, and they will see interference between these two modes of oscillations. So what they will see, the spectrum, the aim is to measure very precisely the energy spectrum of events. And due to these oscillations, you will see something like, due to these 1, 3, or 2, 3 oscillations, they will see modulation of the number of events. Now, depending on mass hierarchy, you will see shift in this oscillatory pattern. So what they will measure the phase of this distortion. So what's precisely is measured, will be measured. And actually this is interference between two modes of oscillation. One is due to this small split. A small split produces long. So essentially, you are sitting in the maximum of oscillations due to 1, 2, and then you see modulation of what you expect. So we will discuss oscillations in probably in the last lecture, and I will discuss this in more detail. So they will measure the phase of this oscillatory picture. Of course, for this you need to have very good energy resolution because you need to see these peaks. And this is why the prediction of the spectrum of neutrinos or antineutrinos is extremely important.
Does UN stand for underground neutrino and observatory?
Sorry? Yeah, that will be underground. Unfortunately, not very deep. That's something like, what is this? 600 meters or so. That's quite substantial. They also have, apart from this ASTROPARTICLE program to detect supernova neutrinos, probably solar neutrinos, but they are not very deep to detect well, say, low energy solar neutrinos, for instance. So now we are moving to a new epoch in particle physics, discoveries and studies of particles at accelerators. But before this, let me give you some general comments. So what we learned from this detection of neutrinos. Not only we have discovered new particles, confirmed the existence of neutrinos, but we see what is the chain already of our understanding of steps to this discovery. Remember, we started with beta decay. Well, by the way, when I described this, you know how many things was behind this picture of discovery of neutrinos. So we already, assume to some extent, right? Let's assume that reactors emit neutrinos. So there are some beta processes in reactors, so they emit neutrinos, then we detect these neutrinos, and then different signals from this detection. So remember, starting point was beta decay. In the early days of last century, people discovered all this type of radiation, then studied beta decay, and these studies led to introduction of neutrino. Okay. So then what we learned is that neutrino, according to Fermi theory, and Fermi theory was constructed, should have this inverse beta decay. On the basis of this inverse beta decay, we actually expect that neutrino, which scatters on protons, should produce neutron and positron. So all this is the picture. If you want it, this is the model of what's going on. And we are testing an experiment this model. Okay. So then there were these ideas, what is atomic reactors. And we can compute what are the fluxes of antineutrinos from atomic reactors. And here we can compute cross-section on the basis of what we know about neutrinos. You see, all this is behind the experiment by Reines and Cohen. Then it was ideas of how what is the effect of positron and neutron. So we know that this has annihilation. And for all this, what is enough is to know what are the masses of these particles and what are electric charges of these particles, what are, say, spins of these particles. Remember, I made this comment, what we mean by the particle, right? So, and all these kind of ideas and notions are behind this type of the discoveries. We know how a neutron behave. We know that we have emission of photons. We know how the photons react in scintillators. So we have this excitation of atoms and molecules, emission of ultraviolet photons. We know then what the effect is behind, then this acceleration of electrons, and then detection and production of the current. You see how many steps and many things are behind this observation. And now the question is all this true? And the fact that we observe these events, which we have predicted, tells us that this picture is correct. Okay, think about this. So how many already notions is involved and these observations?
Error propagation in each process might be huge.
Any propagation, say?
The uncertainty propagation of each process, that's difficult.
Well, so of course we need to take into account uncertainties. So we know what is cross-section. We know that we deal with quantum effect, and therefore we can predict the average number of expected events. Of course, it should be some fluctuations. Right, so for instance, the theory gives us that we need to have, say, 50 events, but then if you kind of take into account quantum nature, already because of this, you will have, say, 50 plus minus 7 or something like this with one sigma deviation. So you can, in one set of the measurements, have, say, 57 events and another 43. This is already where quantum theory enters. So another comment is that in most of this analysis, we are using classical behavior of the particles. So this is quantum system, but in some respects, this quantum system shows up as classical system, and in many of these measurements, we really use this classical manifestations of elementary particles. Okay, so now we are moving to accelerators. And you have some exercises, right? So now information which is useful for solutions of problems. So how do we accelerate particles? We accelerate particles using electric field. Magnetic field doesn't accelerate particles, although when you are discussing accelerators, mostly people are talking about magnetic fields, right? So that's kind of a non-trivial part. But acceleration itself occurs in electric fields. So in electric field, we have the force on the particle, which equals by charge, and the strength of electric field, and the strength of electric field is given by difference of the potentials. V of the x. And so if your particle crosses the difference of the potentials V1, V2, this is V, distance, and so if particle crosses the difference of the potential V2 minus V1, it gained the energy equals charge delta V. Now, we want to have as much as possible acceleration. So, of course, first we studied accelerations at quite low energies, say a few hundred MeVs. This was what in the accelerators in 50s. So we tested what we can test in this energy range, then we move to higher energy range, then higher and higher. And of course to produce new particles, and if we want to search for particles of bigger and bigger mass, so you need to have bigger and bigger energy. So this is kind of a race for these high energies. The problem to accelerate to high energies is that when the strength or difference of potentials becomes bigger than 10 MeVs per meter, you will have discharges. Even if you have well evacuated medium and you apply this high tension, still because you have, say, iron in the walls or cathode or anode, electrons will be put out from these materials and they will produce discharges. So it's difficult to create energy tension, so electric tension bigger than this. Then how to accelerate particles to higher energies? Then you can find what should be maximal delta E. So what is the idea? The idea is to use the same, to use small delta V, but many times. So that you avoid discharges, but still you can accelerate particles to very high energies. Now in this case, delta V total is given by n. This is number of times you use small delta V times delta V. There are two different realizations of this idea, and one is to use many different delta V, and this is what is realized in linear accelerators. So you have on the way of particle many gaps with small delta V, but when particle crosses all this medium, you will get high acceleration. So another idea is to use the same delta V but many times. Many times. So this is what you have in, yeah.
I don't understand why should we avoid the discharges.
Why, sorry?
Why we should avoid the...
But then you will not be able to accelerate particles, so you will not get bigger electric tension because you will have just discharge. You will not create big delta m squared than this. So if you have 1 meter, say, gap between positive and negative charge plates, then maximally what you can get is 10 MeVs. Now, if you start to increase, you will have discharges and never get higher delta V. And of course, in the presence of discharges, you cannot accelerate particles. So they will accelerate just because of discharge. That's it. Now, so that is realized in cyclic accelerators. But for this, you need to have kind of circular trajectory of the particle, so the particle crosses the same gap with acceleration many times. So for this, you need to have magnetic field, which actually bends the particles, create these circular trajectories.
Why not having a linear accelerator with the same length for each acceleration?
We will come to this, I will explain how this works and then you will ask me again. But nowadays we have kind of combination of this idea, so that in accelerators so in LHC there are some kind of zones or sections of acceleration ring when you have these linear type accelerators. We will come to this later.
So when we will have a circular type of accelerators for charged particles, wouldn't charged particles lose energy by radiation?
Yeah, by synchrotron radiation, and I will discuss this. So let me start with linear accelerators. The idea is to use small delta V, many different delta V's. So, what we call with abbreviation Linux. So the idea is to use many different delta V. So the experimental setup is the following. Particles are moving in pipe inside the tube. Which are surrounded by cavities of the following type. Let me draw and then I will explain more. Okay, so this is pipe. And those are these drift tubes or cavities. Or people are calling also clistrons. So they are connected to alternative voltage. So this one is related to this one, Oh, maybe I will write another one. So let me draw yet another one. Alternatively. So that is connected with this. This is connected to this. And then you have here alternative voltage of radio frequencies. Acceleration, yeah?
Why does it have to why is the delta V different from each of the cavities?
So I'm coming to this.
Okay.
Suppose in a given moment t, this is negatively charged, this is positively charged, this is negatively charged, this is positively charged. Acceleration occurs in the gaps. So these are accelerating gaps. This delta V is here, here, and here. So, for instance, we have electron which is moving inside the first this drift tube, and then when it appears here and this gap, it is accelerated. Now, of course, if you have just constant electric tension, then in the next gap it would be deaccelerated, right? So the idea is, so you have delta V here, you have delta V here, delta V here, and they are the same. Because these alternative tubes, they are at the same tension. Now the idea is that when your electron is moving inside this tube, you switch off polarity. And so when your electron is arriving at this second gap, that will be negatively charged and that will be positively charged. And so it will accelerate again. Now the question is, what happens with electron when it is moving here and you change polarity? Tell me. So let me repeat again. So electron accelerated here. Then it is moving inside this tube, and this drift tube, inside this drift tube. And at this moment you change polarity. So what happens? So this tube from positively charged becomes negatively charged.
So just repel the electron away.
More questions? More kind of suggest? Then you will not have acceleration. So because you change polarity, then you will stop your electron.
Inside those between the gaps, there is no electric field.
Yeah,
So what
there is electric field. However, you have no difference of the potentials. So this is the point, that's what and this is the trick people are using. Inside this tube, although you change polarity, but the tube is charged in the same way here and there. So there is no difference of the potentials here inside the tube, and therefore, although you change polarity of your tube, this doesn't affect your electron. Is this clear? Again, what matters is difference of the potentials. If there is no difference of the potentials, then you have no effect. So it's a clear idea, right, to use this. So particle is accelerating here, then you change polarity once it is moving here, and so you again have minus and plus here. When a particle moves here, you again change polarity, and when your electron reaches the second or third gap, it will again meet the same delta V, and will accelerate again.
Then you need a time-dependent frequency. Because then you need to...
No, people are using different lengths of tubes. So,
okay.
right? So, the first cavities, because you have acceleration, right? So the first electron has not very high, it has still some high velocity. However, here is not accelerated sufficiently, and therefore you need to have the size of this gap, the size, such that you know what is velocity of your electron, so that when it reaches this gap, you make a switch of the. So you have the same frequency, but you change the size of this gap. So you have time t1 of propagation here. Now particle accelerated, and therefore it moves with bigger velocity here, and therefore time t2 is shorter. Sorry, and you need to have the same time. So you need to have a longer tube so that your t2 equals t1. So this is t3. So you change, the tube becomes longer and longer, so that the time of propagation within this tube is the same. Okay? Frequency doesn't change. What changes is the size of these drift tubes.
You could do the opposite anyways.
What?
You could do the opposite anyways. By changing the frequency and having the same length.
Well, but it's technically this is easier.
It's easier,
Yeah. Clear? And so the energy of particle has the following behavior, so that the energy, and this is your distance. What happens is the energy doesn't change within the tube, then it increases in the cavity, then again constant, then increases further, then again it's like here. So that is how the energy changes with distance.
You said that in a particular cylinder the potential is constant everywhere.
Yeah.
So for that to happen, the diameter of the cylinder should be much smaller than the length of the cylinder.
Yeah, so I will show you the plots of the figures, actually the real installations. Of course, you will still have some kind of border effects, but mostly what is important that it may not be, say, the peak of your change of the potential, but in any case, you will have acceleration. The second important point you can actually extract from this that you cannot accelerate continuous flux, right? So you need to have your electrons injected in bunches, in the groups. So because suppose it has plus, minus and plus here, and if you have continuous flux of the electrons, then part will be accelerated, part will be out of the phase, correct phase, it will be decelerated. So this is why this acceleration, because what I have discussed is just a single electron, right? So, but when you do this switching off, say from here from plus to minus, it will be minus and plus, and of course electrons which will appear in the gap, in this situation, they will decelerate. So you need also to have kind of certain benches and the time difference between benches. So you need to inject your electrons in certain moments of time so that you will be in accelerated regime, right?
This can work also as a velocity selector for particles.
Sorry?
As a velocity selector, just to choose a specific velocity of a beam of particles.
Oh, this is even more complicated. Imagine that you have here some, of course it should be some system here to inject. So what you are usually doing, you are even cooling first, so that all the particles have the same velocity, very close velocity. Again, if you have different velocities, big distribution, again you will destroy this picture, right? So of course later when they become ultra-relativistic, velocity is very close to velocity of light, then this difference doesn't play a role. But in the beginning it's important to cool, and so they start with the same velocities.
Is there a way to determine optimize the distance of the gap?
Well, of course they optimize this to have maximal acceleration with a given length of this equipment. Now, let me give you some numbers. So what are the frequencies? The frequencies in the early accelerators were radio frequencies, and typically something like 30 megahertz, which is say 3×7 hertz, and that corresponds to lambda, which is c approximately over mu, something like 10 meters. That determines the size of these tubes. So the size of the tubes with this frequency should be of the order of 10 meters. Actually, yeah, something like that, 10 meters. What else? So, some examples. The famous linear accelerator is SLAC, at which a number of discoveries has been done. This is a Stanford Linear Accelerator Complex. It has lengths 2 kilometers, just to have an idea, and there are 240 these drift tubes or klystrons. Now, this accelerator, maximal energy to which you can accelerate particles, and they are usually accelerate electrons and positrons, is from 25 to 30 GeVs. So this is a maximum to which you can accelerate particles. The present day, people discuss new linear accelerators with the name in particular ILC. I'll write it here, ILC, which is International Linear Collider, and it will accelerate particles up to 500 GeVs.
In what country? In what country is it planned?
It's a good question, because still it hasn't been decided. It was first thought that it may be in Japan, then in China. At some point it was discussed to do this in US, but in US they will not do this, so it's not clear. It's under discussion still, and it may not be even happening. But a lot of publications and studies related to this collider. So, using these linear accelerators, one can perform different type of experiments. And one is with fixed target, so that you accelerate particles, electrons or protons, and then put target here and hit the beam onto fixed target experiment. But you can use also this as a collider in the following configuration, and this is actually what is realized at SLAC. They have accelerator tunnel, and with all these equipments, and they accelerate electrons and positrons. So then these particles are injected in storage ring. So using magnetic field, you kind of put particles in these storage rings, and they are moving in different directions. And then you have some area in which these beams are crossing, and you put the detector here, and you study E plus and minus annihilation. E plus and minus annihilation. This is the regime in which SLAC accelerator was working, and we will discuss various discoveries made with this machine. So you can change the energy of accelerated particles, and you can study this E plus and minus annihilation at different energies. So this is storage ring. So of course there are two tubes, but in some region they kind of intersect, and here you have collisions of the plus and minus. Otherwise, so electrons and positrons are moving in this direction, and the electrons are moving in opposite direction with the same magnetic field, and so you have one area of of collisions. Okay? Now let me move to cyclic accelerators. And the idea is to use the same gap, but many times. For this you need to bend the trajectory of particle so that it will cross the same gap, again with a difference of electric potentials many times. So one of the configuration is the following. So you have a single gap between these two semicircles. So this is gap. And you have a difference of the potential between this part and that one, say for instance plus and minus. You inject particle here, somewhere in the center, and so it starts to move in the following way. And here B is constant, so the magnetic field in this direction, and this is constant. This was in the first accelerators of this type. In the very beginning. So what you will have here is that particle is moving in a magnetic field. So it enters the gap, it accelerates, so it becomes of higher energy, and therefore the radius, like more radius, becomes bigger, and it starts to move on this trajectory. On this trajectory with bigger radius, it again enters the gap and accelerates it again, and when it moves in, say, one of these hemisphere, so this plane, then you switch polarity, so it will be accelerated again, and will move to bigger radius, accelerate again, and eventually, so you put here something which extracts your beam from this accelerator machine. So this type of accelerators is called cyclotron. And that machines worked in, say, in 50s. And there were some discoveries made with these machines. We will discuss one of these later. Okay? So in this way you can accelerate particles, say, up to 1 GeV protons, so up to 1 GeV energy. More advanced machines are synchrotrons. And the idea is that you fix radius, but change magnetic field. So here is B is constant, but radius changes. And let me remind that the radius is given by momentum of particle E over B. Okay, if B is constant, then with increase of momentum in the course of acceleration, the radius increases, and so this is why it has this spiral motion. Now, the another idea is to have the same radius and simultaneously change B and P. And this is why it's called synchrotron. You synchronize acceleration process with change of magnetic field. Okay, so what is synchronized? Change of B is synchronized with change of momentum or energy. think any people are eating this. It's not chalk anymore. Oh, huh?
There's some chalk on the floor.
Ah, okay. It's synchronized with increase of momentum. So what you have now the tunnel, which is in the first approximation is circular of a certain radius, actually it's tube, in which particle is moving. So particle accelerates and energy increases, and you simultaneously increase B, and therefore it's always in the same size of the ring. So P T is proportional to B, to change magnetic field. Now in reality what's going on, there are some sections of this ring. It's not everywhere, but there are some accelerator sections where essentially we have kind of linear accelerators type in which you have acceleration. And actually, it's not completely ring. Usually what you have kind of accelerated trajectories, parts, and then like this, then circular, then these. The parts where you have acceleration are essentially linear. So it's like here you have not perfect ring. Now let me discuss some features of this type of accelerators. One is synchronization of magnetic field and momentum of particle. The second one is the acceleration occurs in cycles. Which means that you inject particles, start the process of acceleration, which may take maybe 1 hour or so. Sometimes it's quite long time of acceleration. Then you collide your particles. So let me put here injection. Then acceleration. And then you have experiments. You put your detector somewhere. Along this ring and and then perform studies. So then you have, of course, quality of the beam changes, right? So you have still some lack of focusing, and some particles are out of the beam. So at most you can work with this say 1 day. It's like, for instance, LHC works. So in the morning they inject particles, perform acceleration, and made then experiments, and then after some few hours, 8-9 hours, they do beam down. So put your beam onto some target just to eliminate and to free your acceleration ring. And so next day you start all the procedure again. So we inject particles, we made acceleration, perform measurements.
What kind of targets do they use for that?
Usually tungsten, very heavy elements. And at LHC the beam is so powerful that you essentially burn this material. It's not a joke. So this is kind of cycle in which the experiment works, so this accelerator works. Now, like in the linear accelerators, you accelerate these particles in bunches. So inject particles in kind of short period of time, and acceleration again occurs because otherwise you will not have acceleration if you have continuous flux of the particles. With these acceleration sections, it's like essentially a linear accelerator. You need to have certain moments of time, and therefore you cannot have a continuous flux acceleration, and you have separate benches of the particles. I probably will skip the issue of focusing, which is extremely important because you have these bunches, which are very small. Say for instance, this bunch of the particles is like in a volume which is of the size of the hair of just human hair, and of this size, 10 centimeters. Can you imagine that you have these particles, huge number of particles, like 10 to the 11 particles, which are in this bunch, and you need to arrange things in such a way that this bunch is not destroyed, So, and you have positively charged protons, for instance. Of course, they have some kind of repulsion. And they have very subtle system of magnets which actually focuses these particles. There's also kind of natural focusing process, but this probably I will not discuss.
Is this process the same as we use in electron microscopes to focus, electron beams?
Well, to some extent, yes. So you need to, but this is very sophisticated system of magnets to keep this, all these particles during hours without spread. Otherwise, you are losing luminosity, is what people are saying.
And actually, sometimes the scientists who work at LHC, they say that we have to, attain very low temperatures. Why is that in LHC?
Well, because you want to avoid some kind of thermal motion. Clearly, you need to have this to evacuate this tube, and the magnets to have this so big tension here. The magnets are they are super cooled.
So we need superconducting.
Yes, so you need to have superconducting magnets to have a big strength of magnetic field. Now, important process here is synchrotron radiation. Let me say a few words about this. So one particle is moving not along the trajectory which bends, it emits photons. So and when it moves, particle moves in magnetic fields, so it has a circular trajectory and emits photons continuously. We actually met already such a process when particle moved in electric field. Remember we discussed this radiation energy loss, which is due to, again, acceleration or deceleration of particles, but in electric field. Here is in magnetic field, and there is some difference. Now let me explain this difference. Let me see where I have it. Probably I will write the formula that energy loss, and then explain how these parameters appear here, is proportional up to coefficients to electric charge square, and then an important factor, which is p to the force, momentum of particle to the force power, the mass of the particle to the force power, and the radius square. So this is an important factor which I want to explain to you. So electric charge square is clear, so this is the process with a single vertex due to electromagnetic interaction, and therefore in probability it should appear as E squared. Now, the important parameters which you should remember is this dependence, it's p to the force power. So you see, when you start to accelerate particles, the energy loss increase as a p to the force power. So at some point, your acceleration simply stopped because of this energy loss. It's very fast increase. Another important feature is the mass to the force power here, which means the lighter the particle, the more energy loss, right? And a very big, strong dependence. Remember, in the case of radiation, it was mass square in denominator. Here is mass to the 4, and this is because of this magnetic field origins of this acceleration, right?
Can't we cancel the mass in the momentum from the mass in the denominator?
So which means that for light particles, if you want to accelerate to higher energy like electrons, better to use linear accelerators. Okay, for heavies, that's okay because you have heavy protons. This is why we are using synchrotrons for protons. Although we had this lab accelerator, and lab accelerator was just for electrons and positrons, but it has the same radius as LHC, actually in the same tunnel, 27 kilometers circumference. But the maximal energies were something like 100 GeVs. And we cannot accelerate more with this, while for protons, we have acceleration up to 6 TeVs, which is much, much higher. Now let me explain these factors. And then the difference between radiation energy loss and the synchrotron energy loss. So let us find acceleration and the energy loss, as it was also in the case of radiation energy loss, is proportional to acceleration squared. If you do this for quantum effects, you square usually. So let us find acceleration. The force is given by dp over dt. This is force is given by the change of the momentum in the unit of time. And let us look at the trajectory of particle and what is this delta p in the unit of time. So suppose in some moment of time particle was moving in this way, and in the unit of time it turned out at this point of the trajectory and some momentum became like this. So this is alpha angle, this is radius, and then let us find what is delta p. Delta p equals p multiplied by alpha, right? The first approximation. And so alpha is given by velocity of particle over the radius. In the unit of time, particle will have this way, which is given by just velocity, right? This is velocity, if you consider this in the unit of time. And so, therefore, this angle alpha is velocity over the radius. Now, velocity of particle is given by momentum over mx, the mass of the particle, and therefore alpha is given by momentum over mass of the particle x and the radius. And therefore the force will be given by this delta p, if it is p in the unit of time, and so it will be given by p, and then multiplied by alpha, it will be p squared mx radius. And therefore acceleration, by the way, immediately I can call your attention to this. So here we have mass in the denominator. The force is inversely proportional to mass. And this is different from radiation energy loss, where the force, remember, was given by just the electric charge and electric tension. So in the case of radiation energy loss, the force didn't depend on mass. Here, it inversely proportional to mass, and this is the origin of this higher power of the mass in denominator. So that acceleration is given by p squared over mx squared and that radius. And then, as we decided in the case of quantum level, if this energy losses are proportional to h squared, and I will get this dependence. So this is the origin, or this is the main factor here.
In this case, you are considering non-relativistic case, so it's also acting.
Well, so you see, this is kind of idea how to get these parameters, right? Now I'm applying this also to relativistic case. In the same way as we derived expressions for radiation energy loss. So the physical difference, of course there are derivations, and also with this relativistic effects, and then some emittance factor, coefficient appears, etc. in more complicated form. However, dependence on the most important parameters is this one. P to the fourth and mx to the 4. Remember, in the case of radiation energy loss, we just had here mass in the first power, not square. So this is because of the mass dependence on the force itself.
The acceleration that you have just derived, just the centimeter acceleration, which is v square over r, and you just write v is equal to p over m.
Yeah. So
Can we understand that it is only proportional to the square of centimeter acceleration?
So the force is this acceleration is force over the mass, and now going to quantum and relativistic level, I put here a squared, not a, as it's in classical way. So this is kind of the trick, but it works, and just to give some idea how things can be derived. Because I have no time to have this, probably not much sense. If someone will work on this, then of course that is important. Now, so what is left, I will discuss tomorrow. What is left is this luminosity and some characteristics of accelerator. Questions? So this kind of synchrotron radiation losses is key element which actually gives restrictions on using of this technique, and one should always remember this planning new accelerator. By the way, it will be this week. It will be talk by colloquium by Peskin, who will talk about possible future accelerators, synchrotrons, which would produce 30 TeVs. We will discuss even 100 TeVs energies for future accelerators.
So in what range does this synchrotron radiation lie normally for large accelerators? I mean that in X-rays or gamma rays?
Good question. So that depends on energy, of course, of particles. And it can be from very soft radiation, but it can be, yes, it can be depending on very high energies. It becomes in the X range.
So do the synchrotron radiation have any use?
Oh yeah, sure. We have even synchrotron here for medical purposes. Yeah, from X and gamma. So this is one of the sources of this type of the radiation. To use this in medical services, purposes.
When you mention the energy of accelerators like slug and leak, these energies are for a certain particle, say electron, or are particle dependent?
Which you are?
For example, the energy of a slug.
Slug, yeah. This is electron and positron. So
electron
that's
and positron.
yeah.
But
So
if I have a proton,
now, for proton, since the same potential, you may have the same energies. Yeah. The energy is just given by charge multiplied by delta V, and then you multiply this by the number of gaps. But it is easy and more economical way to accelerate protons in synchrotrons. By the way, in all the accelerators, at the first pre-accelerator, people are using linear accelerators. Even at LHC, so actually there's a several steps of acceleration, like in LHC, you have the first you accelerate using LINAC, small size LINAC accelerator. Then what happens is that is injected in PS, old accelerator ring, then SPS, another ring which accelerates up to several hundred GeVs, and then everything is injected in the main ring. Right. Okay, so yeah, I want to talk today to other guys. I don't know who is the next. So I think you let me switch. Oh.